the early 20th century, San Francisco faced a geographic barrier that defined its limits. The narrow strait, known as the Golden Gate, separated the city from the northern counties, its waters deep, cold, and violently unpredictable. Ferries carried passengers across the channel each day, but they were slow, vulnerable to fog, and insufficient for a growing region. The idea of building a bridge across this stretch of water was widely dismissed as unrealistic. The currents were powerful. The winds could reach dangerous speeds. The seabed dropped sharply into depths that engineers of the time had never confronted on such a scale. Many experts declared it impossible. Some warned it would collapse under its own weight. Others argued the financial risk alone could devastate the region. And yet, in the midst of economic uncertainty and approaching global crisis, the project moved forward. The Golden Gate Bridge would not only test the limits of engineering, it would test the willingness of a society to invest in something that might never succeed. How much did it truly cost to turn this impossibility into steel? And could such a project even be realized under the conditions of today? When the proposal for the bridge gained political support, enthusiasm was not universal. The estimated cost of construction was approximately $30 million, an enormous sum for the early 1930s. At the time, the United States was entering the Great Depression. Banks were failing. Unemployment was rising rapidly. Public confidence in large infrastructure investments was fragile. To finance the project, local counties agreed to issue bonds, effectively placing the financial burden on the surrounding communities. If the bridge failed, technically or economically, taxpayers would bear the consequences. $30 million in 1930 represented a staggering regional exposure. Adjusted for inflation, the equivalent today would amount to several $100 million. For a sparsely connected coastal region, this was not a routine infrastructure upgrade. It was a high-stakes commitment that could determine the economic trajectory of the entire Bay Area. Major financial institutions in New York initially refused to back the bonds. The risk was considered too high. The location was too dangerous. The return on investment was uncertain. Eventually, a single banking group agreed to underwrite the bonds, allowing construction to proceed. It was a decision based not only on engineering feasibility, but on projected traffic flow, toll revenue, and long-term regional growth. This financial structure transformed the bridge into more than an engineering challenge. It became a collective wager, a calculated bet that increased connectivity would generate economic expansion strong enough to repay the debt and justify the risk. The bridge district assumed that future toll revenues would cover interest payments and gradually retire the debt. If traffic projections proved overly optimistic, the financial strain could persist for decades. The project, therefore, required not only structural confidence, but economic foresight. Financing the bridge was only the beginning. The greater challenge lay beneath the surface of the Golden Gate Strait. The channel was nearly 1 mile wide, with water depths reaching more than 100 meters in certain sections. Powerful tidal currents moved through the strait at speeds capable of destabilizing construction equipment. Dense fog reduced visibility for much of the year, while strong Pacific winds exerted constant pressure on any vertical structure. Engineers had to calculate not only static loads, but dynamic forces created by sustained wind exposure. A suspension bridge of this scale behaves like a flexible system rather than a rigid frame. Every gust of wind introduces oscillation, and every oscillation must be absorbed without structural failure. In an era without advanced computer simulations, these calculations relied on physical modeling, empirical testing, and mathematical approximation. To anchor the suspension towers, engineers had to construct massive foundations in open water. Temporary cofferdams were built to create dry working conditions and operation exposed to unpredictable waves and shifting currents. Workers labored high above the water, often in cold and hazardous conditions. The bridge's main span would eventually stretch over 1,200 meters, making it the longest suspension span in the world at the time of completion. Designing cables capable of carrying such weight required careful calculation of tensile forces, wind loads, and long-term material fatigue. Each of the two main cables contained more than 27,000 steel wires, spun in place across the span. The margin for miscalculation was minimal. Chief Engineer Joseph Strauss and his team collaborated with structural specialists to refine the final design, reducing excessive weight while maintaining stability. Innovations in cable spinning and aerodynamic consideration helped prevent oscillations that had plagued earlier bridges. Safety measures were unprecedented for the time. A large net was installed beneath the construction zone, reducing fatalities compared to similar projects of the era. The Golden Gate Bridge was not built under ideal conditions. It was built in defiance of them. The true costs. When construction was completed in 1937, the final cost of the Golden Gate Bridge amounted to approximately $35 million. Remarkably, this figure remained below the original budget estimate, an unusual outcome for a project of such scale and complexity. In 1937 currency, $35 million represented an extraordinary public investment. Adjusted for inflation, the equivalent today would range between $700 and $800 million, depending on the method of calculation. However, inflation alone does not capture the full economic contrast. Modern infrastructure is shaped by environmental regulation, seismic standards, and expanded labor protections that significantly increase baseline costs. Comparable suspension bridges today frequently exceed multi-billion-dollar budgets, yet the financial significance extends beyond inflation alone. Material prices, labor standards, environmental regulation, and seismic engineering requirements have changed dramatically since the 1930s. Steel production was less expensive relative to wages. Safety standards, though advanced for their time, were far less stringent than modern requirements. Environmental impact assessments did not yet exist in their contemporary form. If the same structure were proposed today, with identical dimensions and performance expectations, the total cost would likely exceed several $billion. Some estimates suggest that a modern equivalent could approach $3 to $5 billion, once regulatory processes, design review, and compliance measures are included. In addition, contemporary urban projects often require years, sometimes decades, of planning, litigation, and environmental negotiation before the first foundation is laid. The financial exposure is therefore extended over a much longer preparatory phase, increasing uncertainty and compounding investment risk. The original bridge was therefore not merely affordable for its time. It was built within a financial environment that allowed ambitious infrastructure to proceed with fewer procedural barriers. Its cost was immense, but the economic conditions of the era made such ambition structurally possible. Would it be possible today? If the Golden Gate Bridge were proposed in the present day, the question would extend far beyond engineering feasibility. Modern infrastructure projects operate within an environment defined by environmental protection laws, seismic safety standards, and complex public review processes. Any large-scale construction in the San Francisco Bay would require extensive environmental impact assessments, marine ecosystem studies, and multi-layered regulatory approval. Federal environmental legislation, such as the National Environmental Policy Act, would mandate comprehensive review procedures, including public consultation and potential legal challenge. Marine habitats, shipping routes, and coastal erosion patterns would be examined in detail. Each phase of approval could introduce delay measured not in months, but in years. California's strict seismic building codes would demand advanced reinforcement systems designed to withstand major earthquakes along the nearby fault lines. Materials would need to meet contemporary certification standards. Worker safety regulations would be far more comprehensive than those of the 1930s. Each of these requirements increases cost, but more importantly, they extend time. Major infrastructure projects in the United States today often spend a decade or more in planning, litigation, and environmental review before construction begins. Preliminary studies alone can consume years before financing is finalized, while inflation and policy shifts expand projected costs. Political negotiation, community opposition, and funding debates can further delay progress. The financial exposure of such a project would therefore accumulate long before steel touches water. Private bond financing alone would likely be insufficient. Federal participation would almost certainly be required. In strictly technical terms, the bridge could be built today. Modern high-strength steel, computer-aided wind tunnel analysis, and advanced seismic dampening systems would reduce structural uncertainty. From a purely engineering perspective, the challenge is manageable. Based on comparable large-scale suspension bridge projects in the United States, total planning and construction costs today could realistically range between $3 and $5 billion. This figure would include extended environmental review, seismic reinforcement, insurance structures, and modern labor standards. The financial threshold alone would likely require multi-level federal and state coordination before approval. Modern materials and digital modeling would allow even greater structural precision. Yet the economic and regulatory framework has changed profoundly. The original Golden Gate Bridge emerged from a moment in which ambition, risk tolerance, and procedural simplicity aligned. Whether such alignment still exists is not a question of engineering, but of political and societal will. When the Golden Gate Bridge opened in 1937, it was celebrated not only as an engineering achievement, but as a statement of resilience. The United States was still emerging from economic depression. For the Bay Area, the bridge represented connection, mobility, and renewed confidence in large-scale public ambition. Over time, its function extended beyond transportation. It became an international symbol, recognized instantly across the world. Its distinctive silhouette and color transformed it from infrastructure into identity. Few structures achieve this transformation. Most bridges remain functional elements of transportation networks. The Golden Gate Bridge, however, entered cultural memory. It appeared in film, photography, and political imagery, gradually shifting from utility to emblem. Yet the symbolic power of the bridge should not obscure its original purpose. It was built to solve a logistical problem, to connect communities separated by water. The economic consequences were substantial. Property values in surrounding regions increased as accessibility improved. Commuting patterns changed, integrating previously distant communities into a single metropolitan sphere. The bridge altered not only movement, but economic behavior. Increased traffic flow accelerated regional development, strengthened trade, and reshaped patterns of settlement around the bay. What began as a high-risk financial and engineering venture evolved into one of the most recognizable structures of the 20th century. The Golden Gate Bridge demonstrates how infrastructure, when successful, can redefine both geography and perception. The price of ambition. The Golden Gate Bridge was not inevitable. It was proposed in uncertainty, financed in economic crisis, and constructed under conditions that many considered unmanageable. Its final cost was immense for its time. Its technical demands were unprecedented. Its success was never guaranteed. Failure would have imposed lasting financial strain on the surrounding counties. The decision to proceed required confidence not only in steel and mathematics, but in long-term regional growth. Yet the bridge stands as proof that infrastructure is not shaped by engineering alone. It is shaped by collective risk tolerance, by a society's willingness to commit resources to a future it cannot fully predict. Today, the financial and regulatory landscape has grown more complex. Ambition is filtered through extended review, layered compliance, and cautious budgeting. The question is therefore not whether such a bridge could be built again. Modern technology makes that possible. The deeper question is whether the same alignment of risk, confidence, and decisiveness still exists. Some structures connect land. Others connect eras. A few alter the trajectory of the regions they serve. The Golden Gate Bridge did all three.